Okay, good afternoon, everyone. Today's our sixth meeting, and today we will be discussing guiding diffusion algorithms, guiding in order to achieve something, obviously. What I'm going to do now is to start by motivating the notion of guidance, which kind of guidance we are after, and then we'll dive into two versions of guidance that are aiming to produce specific kinds of images, classifier guidance and classifier-free guidance. And then we'll talk about text-to-image methods, something truly very hot that is happening these days, and it's tightly related to guidance, obviously. One thing that is very much missing in this lecture is guidance by measurements. This is related to inverse problems, and we will dedicate a complete chapter for it next week. Okay, so let's dive in. And at the moment, I would like to just motivate the general concept of guidance and what kind of guidance can we expect to see. So let's start with a specific type of diffusion model. I'm starting with ALD, annealed Langevin dynamics, but it doesn't have to be. It could have been DDPM just as well, or DDIM to that matter. You have such an algorithm that aims to sample from P of X, the probability density function of, in our case, images. Here is the algorithm. I remind you, it's an iterative algorithm that starts with noise, outer loop that changes the sigmas from very large sigma to small sigmas. This is the annealing. And an inner loop that does Langevin steps per each of those sigmas with this iterative equation that keeps updating the x's based on the score function, the score that is blurred with a sigma j as the blurring effect. So it starts very blurry and slowly narrows down towards the true distribution. And we have seen that this score function is approximated using a denoiser, something that we train ahead of time. The denoiser, in the case of ALD, is trained by showing it images that are contaminated by additive noise with varying levels of noise, Gaussian noise, and we clean up the noise. Basically, x0 hat is the cleaned version. This is the D that appears here. And then the denoiser can get the sigma j as a side input in order to know what kind of noise it is fighting. All this is old and new and seen, and we have discussed it very much. So nothing here should surprise you. By the way, if you take K to be 1, then basically the inner loop just does one step, and then you are looking at something very close to DDPM. Very nice. Okay, now I could, for example, do all this for images taken from the ImageNet dataset. ImageNet dataset is a dataset of 1 million images that have all sorts of content. And by training denoising on those 1 million images, I'm basically preparing myself to treat images of the same type. The thing is, ImageNet comes with labels. Every image is accompanied by a label, one among 1,000 possible classes, that tells us whether this is a dog or a cat or which kind of dog, or a car or truck, many classes like that. So here is my question. What if I would like to create specific breed of images? For example, what if I want to create only goldfish images or only Arctic fox images, etc.? What should we do then? This is the guidance, the first version of guidance that we would like to look at. One thing to understand here is that we have 1 million images in ImageNet, 1,000 per each class, and altogether is 1,000 images per each class times 1,000 classes, getting to the 1 million images that we have. Good. So how do we do this guidance? Here's a dumb answer. Dumb, but possible. Let's train 1,000 denoisers. Each denoiser will train on a specific class. And so if you want to create Arctic fox images, bring the denoiser that have seen only those images, and hopefully it will produce the proper type of images belonging to this class. You could do that. But this is a very poor approach. Why? Because of several reasons. First, the amount of memory required, the amount of training work required will be huge. Training 1,000 denoisers is simply too much to ask. Secondly, I told you there are 1,000 examples per each class, so you don't really have enough examples to train on. And this connects lovely to the next point, which is those denoisers are not totally detached. When you clean up images of one class, you have a lot that you have learned that can serve you in denoising the other classes. So can we basically merge forces and do something smart so that the denoisers are basically talking with each other? The answer is yes. Here is an alternative, one that actually works. Let's train a conditional denoiser, a denoiser that gets on top of the noisy image and the level of the noise, it gets also the class. So basically, when the denoiser knows that it is cleaning an image that belongs to the Arctic Fox class, it will do something to benefit it in order to create better looking, cleaner image. And therefore, this denoiser will be the combination of all those 1,000 denoisers. Surprisingly, this simple idea works great, and we will talk about it later on today. At the moment, I'm just giving you intuition. What are we doing here when we are deploying such a denoiser? We are essentially asking to sample from the conditional probability of the images given the class. So for the duration of today's talk, we will be sampling from posteriors of or conditional probabilities of the images given something. And at the moment, this something is the class that we aim to generate from. Okay, so this was case number one. Let's talk about case number two. Again, I'm starting with the ALD, but it doesn't have to be. It could be DDPM or DDIM or whatever. Okay. What if I'm looking at the following problem? Someone gave me this black and white image and tells me that I need to revive the colors. I need to return the colors to this image, okay? Not just creating an image with colors of a parrot, but creating an image of a parrot that this would be the gray value version of it. So this is what I'm after. This or maybe other colorization of this image exactly. Okay, so basically here as well, we are trying to sample from P of X, but conditioning on the given image Y, this gray image that sits as a reference that we have to refer to. Okay, basically, again, just like before, we are sampling or we are asking to sample from P of X given Y. So here is the thing. There are many, many possible images in the image manifold. Most of them are irrelevant because their gray version is not aligned with this image. Among all those images, there is a group of images that have non-zero probability for explaining this grayish image. Only those are coming into account when I'm sampling from this posterior. Okay? So the question is, how do you take Y into account? This is something we will deal with quite heavily next week. You have to understand that what I've done here is just giving you a specific example of many possibilities of something more general that is called inverse problems, and we have discussed them before. The more general structure would be like this. There is an ideal image X that you don't get to see. You get to measure something related to it. Why? Why are the measurements? For example, in our story, why is the gray value image? This conversion from X to Y is formulated using P of Y given X, the likelihood function. Why is it a likelihood function? It could be deterministic. You don't have to be afraid of it. It could be also stochastic. For example, if there is noise in Y, then this will be stochastic. But in most general terms, this is the probability of getting Y given X. And you're getting Y. Now, given Y, you're trying to come back to X and get X hat that could explain Y. You are not hitting exactly the original X, you might hit yet another one. Just like in the parrot story, I can think about other colorizations that make sense. In fact, think about it. In this situation, you could create various possible solutions and all of them will be valid. So you're looking at an inverse problem where you might have more than just one possible solution. And again, the question is, how do you condition your diffusion in order to take Y into account? And just to give you the broader picture, There are many, many inverse problems. Denoising is an inverse problem. You are giving me this noisy image, and I'm supposed to give you a clean and crisp looking image that explains it, in the sense that the difference between the two looks like white Gaussian noise, or deblurring, where I'm getting the blurry version of the image with noise and I'm trying to recover the image, or in painting, where I'm filling in the missing values, or the mosaicing. We have been through this. Tomographic reconstruction, where you have projections and you want to take basically the reverse operation in order to come back to the image that has these projections. Super resolution, where you have a low resolution image and you want to enlarge it while creating something that is crisp and beautiful, etc. All these and many others are inverse problems. For example, here are more such inverse problems that are not so easily modeled. For example, JPEG deblocking. An image went through compression, decompression, and the compression was severe, was really deep, to the point where there are huge degradations and the image is poor looking. And you're asking yourself, what could be the original image that explains this? And you get something like this, and maybe other solutions. Or, for example, conversion from visible to infrared. I'm showing you an image that is being photographed using regular camera, and I'm asking, how would it look if an IR sensor would have been sensing it? And the conversion might look like this. Or stylization, where I'm giving you this image and I'm asking, what is the style version of this image if the style I'm trying to incorporate is such and such? So now I'm getting into inverse problems that are truly bizarre, in the sense that there is no mathematical connection between the x's and the y's, and yet they are valid. Or here is another one. I'm giving you a daylight image and I'm asking, how would it look at night? Okay, so before and after. All these are inverse problems. We will talk a lot about them next week. So let's just leave this aside. But yet, remember, this is another way where we need guidance. This was case number 2. Case number 3 is really fascinating. It didn't exist 2 years ago. This is guidance by prompt. So basically, you give me a sentence, a description, or let's call it a caption, that describes verbally something that needs to appear in an image, and then you create an image out of it. Okay? All these are images created by Imagen, a tool that was developed by Google. And basically, the sentence drives the synthesis. A strawberry mug filled with white sesame seeds. The mug is floating in a dark chocolate sea, and you let the diffusion do its thing with conditioning on T, and you get this. And look at the other images. Let's look at it, for example. A photo of a corgi dog riding a bike in Times Square. It is wearing sunglasses and a beach hat, and you get this image. You have to understand, if you run the algorithm again, you'll get a different image of the same flavor, of course. So here as well, we are looking at conditioning or guiding the diffusion. This is a very daring task, something that we couldn't do 2 years ago and before. It's fascinating, and yet it is totally possible these days. Diffusion models brought a revolution and enabled this to the levels that we see in these examples. An extremely angry bird, and you get this one. Again, what we do here is to sample from the conditional probability of x given t. Now, t is the prompt, and the question is, how do we do that? And we'll talk about it today. This will be our last portion of the lecture today. Okay, so just to summarize, we start with a generic diffusion model. It could be DDPM, ALD, whatever. It has all sorts of hyperparameters. It can generate images out of P of X. Now we want to augment this algorithm somehow with a conditioning suit, such that it is able to condition the synthesis on class or on measurements. You get poor measurements and you want to create a sample. Or you get a prompt, a dog looking in a mirror, seeing a cat. And the question is how to do that. What are the tools we have in order to make it happen? Of course, what is this part? Now, in the following, I'll discuss the concept of classifier guidance and then classifier-free guidance. Both are serving the first, this class story. And then we'll jump straight into the last portion where we condition things on prompt. I'll do it by describing the work of Imagen as an example. As I already said, inverse problems is a very wide topic. It deserves a chapter of its own, and therefore we will do it next week separately. And I should add, these three are not the only conditioning that you can think of or guidance that you can think of. For example, there is another guidance that says, here's the composition of the picture. Please create something that has a house on the left, mountains on the right, and something else. And you can create images out of it, etc. So all sorts of conditioning. It's a general concept. Okay, so let's dive in. Let's talk about classifier guidance. And again, I'm starting with ALD. And again, it's not critical. It could have been the DDPM. So again, ALD knows how to sample from P of X. Here is the algorithm. We have seen it. This is the approximation of the score. I remind you, a denoiser is playing a major role here. This is the only learned part. And this is it. We have seen all of this. And now the question is, how do I squeeze conditioning on C? And if, as you saw, what I just did is to replace only one thing. I'm changing the probability here from the probability of xk to the probability of xk given C. So basically, all we need to do is to replace the score by a conditional score, okay? Which immediately says that this is no longer relevant. We cannot use it because it's not handling the conditioning C. So we do have to find a way to serve the knowledge of C and its influence on the algorithm. And the question is, what shall we do? Here is a way of doing it. This is the classifier guidance approach. The idea is this. Is this what you want? This is the conditional score. Well, how about using base? Remember, probability of X given C is probability of C given X times probability of X divided by probability of C. Now, if you take grad with respect to X of the log, first, the log will turn everything here to additions and subtractions. And then the gradient will take the grad of the first element, the second element. The third element will vanish because gradient of this doesn't depend on X and it will vanish. So here is what we get. Grad log of this, which is the expression we are after, is basically the sum of the two nominator elements going through grad log, okay? Now, surprisingly, this part that would have been devastating in regular times is actually solved for us. This is exactly the score that we are familiar with. We can do it with a denoiser. We are well equipped to handle it. And the question is, what is this? What do we do with this? Any idea? What is this? What is it saying?
Classifier.
Exactly. Why classifier, Chen?
Because the classifier attempts to, it outputs a probability distribution over the classes given X.
Wonderful, exactly. So let's go there. So this red part is exactly, in words, it is the probability of X belonging to class C, okay? Which is exactly what classifiers are supposed to do. What kind of classifier? Let's be exact here. I'm thinking about probabilistic classifiers, ones that produce at the output values that are proportional to the probability. And soon I'll show you how such classifiers are created. And so if I have such a classifier, I'm well equipped. I can use them in order to come up with this expression. In fact, what I'm telling you here, I'm running ahead of myself here, I'll use such a classifier and I'll take the output and I'll take a derivative of it with respect to the input. This is what I need to do. But just before going there, there is the sigma here. What does it mean, this sigma? What is the implication of this sigma on us? Anyone?
It means that the denoiser parameters have to be tied in some way to the classifier parameters.
So it's not a denoiser parameter. It means that the x's that we are looking at here are what? Are noisy. Are noisy. So basically, what I do need is a unique kind of classifier that can work on noisy versions of images in order to work with P sigma as it's written here, okay? So we need to train ahead of time some sort of a probabilistic classifier that can cope with noisy images with varying levels of noise because sigma is varying. And yes, this machine will be the one that will produce for us this guidance. Okay, so this grad log is basically a backpropagation gradient of the classifier that we will be coming up with here. And don't be alarmed, we are now turning to explain this very slowly in order to show exactly what we are supposed to do. So 2-3 slides on this in order to make it totally clear. Okay, so I'm starting from the very beginning. Someone gave you a data set of images and their labels. And I remind you, the labels are deterministic. This is a dog, this is a cat, this is a truck. So basically think about CK as basically one hot vector. So if this is ImageNet and there are 1,000 possible classes, every CK will be a vector of length 1,000, where all the elements are zeros apart from one that is 1. Okay? I'm training a classifier. The classifier has capital C. C is 1,000 in our story. Capital C outputs, those are the logits. And they are approximating the log of the probabilities, exactly what we wanted, including the log, okay? This is how it works. How do you do it? Here is what you do. You use the cross entropy. You minimize the parameters of the classifiers, this phi that governs the logits. You minimize basically the cross entropy between two distributions. What distributions? CK, those one hot vectors, and the log of P of C given X that comes out for a specific example XK. Okay? Cross entropy is defined in the following way. This is the expression that we will eventually be using as the loss. Don't be alarmed. Let's explain it. So here is the cross entropy. Cross entropy in general for two discrete distributions, we have discrete distributions, is basically the sum of pk log of 1 over qk. If you don't want to put the 1 over qk, you put the minus here. It's just the same. This is the cross entropy. We'll soon tie it to Kullback-Leibler. This is what we are trying to minimize, okay? Or if you remove the minus, this is what we will try to maximize. pk is these one hot vectors. So in this summation, if this is one hot, only one element survives. What element? The log of Q in the proper place, which explains why in this summation only one element exists. We have only the logit in the proper class, CK. Now I remind you, the logits are log of probabilities and they are not normalized. So here is what we do. We take the logit, we take exponent, we normalize with all the other logits, then we get the probability of having QK, then we take the log, and this explains the whole expression. Now, if you are wondering about the cross entropy, this is something that is commonly used in training classifiers, and it is tightly connected to Kullback-Leibler. I mean, for you, it might be more intuitive to think, let's make the Kullback-Leibler divergence between these two distributions minimal. Well, think about it. What do we do here? Kullback-Leibler between two probabilities is pk times log of p divided by q. In our case, well, let's open it up. So it's sum of pk log pk minus sum of pk log qk, which is exactly, this is the cross entropy. Now, the first term is a constant. Basically, this is the entropy of our one hot vector, which is basically 0. So basically, this is not just a constant, this is 0. So minimizing Kullback-Leibler is just like minimizing the cross entropy. And so this is what we did here. And when you finish, when you train like this with this horrible looking loss, you are basically training your machine to produce logits that are aiming to be approximations of the log of the probabilities of belonging to each of the classes. Okay, so here is what happens. You have an image, it goes through this classifier that has been trained, you get logits. Those are proportional to the log of the probabilities. You have a softmax operation that takes you to actual probabilities by normalization. Okay, just like we did here in the expression. So here is what we do now. Let's come back to our story. We need to come up with this grad log of p sigma of c given x. What do? We take we take the logits in the proper class C, and we take a derivative of the output with respect to the input. Basically, we ask the image in the input, what should you do? How should you change infinitesimally in order to change the output at position C? Okay. Now, instead of notice that there is no log because age is already with the log. Now, the better way to do it is actually to go after the softmax so that you work with normalized element, and this is how it should be done. Now, in doing so, you assume that your classifier is probabilistic. in the way you have described, and you assume that it knows how to operate on noisy images. So you will be operating it with a proper sigma j, okay? And we have said that using the logits, the output, and computing the gradient, and this gradient is back propagation over the classifier, and once you have it, you can squeeze it into the algorithm. And now let me show you the algorithm. Here it is. This is it. The regular bluish part is how you use ALD regularly, and now you have a correcting term that says add this in order to drive your synthesis towards a specific image of the class C. And so here is what we do. We approximate the denoiser, approximate the score function using a denoiser regularly, and we approximate this vector using the gradient of the logit that comes in location C in the classifier that we trained. So basically, we take many noisy images, design a denoiser or train a denoiser for them. We also train a classifier of the form we have seen. And with it, you have a lovely way of guiding your algorithm towards specific classes. Okay. One note here that I would like to bring up is the following. In computing the blue part here, I'm basically applying a denoiser. And so if I'm applying a denoiser, I'm basically getting a clean version of the image x0 hat. I remind you, this is exactly the effect of denoiser. Guess what is the clean image? If you have a clean image, you can outsmart this algorithm that I've just described and say, you know what? Let's feed the clean image to the classifier. Why should I feed the noisy version of it? And so one classifier that has been trained only on clean images can be used instead of the more sophisticated classifier that I'm showing you here. Now the question is, should we do it or not? Let's keep this question open. At the moment, it seems like something that is worth doing. Later on, I'll convince you that actually you might not want to do it, but we will see. Let's proceed. This paper from 2021 is the one that introduced this notion of guidance using classifier. Here is the zoom in on the abstract. We consider the 3 applications. Never mind that. Let's go to the second sentence. When Y represents class labels, these are our RCs, we can train a time-dependent classifier, time-dependent, basically sigma-dependent, if you like, PT of Y given XT, exactly like we did. XT is the noisy image, Y is the class, and T says this is the blurry probability. For class conditional sampling, since the forward SDE is tractable, we can easily create training data. So basically, they actually show you that they can train on noisy version of images, and that's all for the time-dependent classifier by first sampling X0Y, etc., etc. So exactly what we described. Work that followed up took this concept and noticed that it's not working well enough and started to squeeze better results from it by doing the following. They took this expression that we have just described and they multiplied it by a scale that is bigger than 1, 3, 4. It varies from one walk to another. And they noticed that if they take this S and squeeze higher values with it, they get more pronounced results. That's more beautiful results. This is really strange. I've seen statisticians make joke about it and say that this is the new Bayes rule, where instead of the regular Bayes, you have this conditional with the power of S here, which is, of course, nonsense. So why do this? Why do the scaling? Here is a little bit of intuition to explain it. Look at this probability density function, P sigma of C given X, and assume that C is actually a continuum instead of being discrete. And here it is. Probability of P sigma of C given X is something that looks like this. So this and this are the most likely C's for the X that we are looking at. This is for S equals 1. What happens if S is below 1? Then basically the function becomes milder. And then you are basically reducing the effect of the guidance and letting more freedom to the algorithm. And in the opposite, when S is bigger than 1, you're pushing things up and down more violently in a way, so that it's becoming more extreme. And so it will push most probably to this place here in the area. So you're creating something narrower, sharper, but more pronounced. And so people have been using it and playing with it. And I'll come back to this later on as we move to the classifier-free guidance. Now, people starting working with classifier guidance notice that it doesn't really work so well, and it creates all sorts of artifacts. And then trying to understand what's going on, they notice the following two things. First, when you train a classifier, and this is something you should know, you cannot trust it to give you balanced and calibrated values of probabilities. Classifiers in general tend to be over-optimistic with their outputs. They tend to extremize the values and suggest that the probabilities are higher than needed. And so you need some sort of calibration. This is easy. All you need to do is to dedicate a validation set and try your classifier on it and tune in all sorts of ways the output so that it is calibrated. There are ways to do so. So this is one thing. And this is important, as otherwise you're using values that cannot be trusted. Something far more sensitive is the following. We are taking a gradient of a classifier. Now, we do know already for 10 years now that gradients of classifiers are looking horrible. They look horrible. Let me remind you why. There is something called adversarial attacks. This is the work of Szegedi in 2013 and a lot of papers that came afterwards. The message is the following. If you had a classifier and you want to attack it, what do? The classifier sees an image and says, this is a dog. So I'm asking, what is the minimal change in the input image that will make it less of a dog? You know what? That will make it a camel. Turns out that when you want to answer this question, what you do is to compute exactly the derivative that we asked for. And what this paper noticed is that when you do these derivatives, you get something that looks like pure noise. And so with very small additional noise to an image, you can change its classification. This is the discovery of that paper from 2013. For example, if you start with a panda, that the classifier believes that 60% confidence it is a panda, there is specific noise. In fact, the gradient of the classifier times very small epsilon, so small in fact that when you add things, you get an image that is totally panda. And now your classifier will believe that this is actually a gibbon with total confidence. So just to summarize, in order to attack classifiers, we compute exactly the same derivative. And we saw, we experienced the fact that these gradients are basically noise, pure noise. So why should we trust this noise to guide us? Okay, this is really strange. You have a great looking classifier. You have just finished training it. It has terrific accuracy of 90% and beyond. And suddenly it gives such horrible gradients. Why? Why is it so easy to attack? Here is an explanation that came from Weizmann Institute, the group by Adi Shamir. It's called the dimpled manifold model. And it says the following. Imagine that we are classifying images that sit on a very low dimensional manifold. In our demonstration, the manifold is 1D, and images are separated between dogs and cats in this manifold. And as it so happens, this is how they are separated. Okay. Now, if you want to come up with a classifier that will tell you these are dogs, these are cats, this is what you're supposed to do. You're supposed to create some sort of barriers that says to the left, dogs, to the right, cats, etc. Okay? Well, this is not what neural net do. When you train a neural network, and the neural network works in the embedding space, which is high dimensional space, in our case, just 2D to illustrate, and the dimensions of the manifold themselves is very low, the neural net will try to do something much simpler because energy-wise, it's worth much more to the neural net to come up with a separating hyperplane or separating surface that lies almost on the manifold, something like this. Okay? Notice this is a perfect separation. Everything below is red, everything above is green, the separation is wonderful. But now when I'm computing gradients, the gradient of this point will simply ask, what do I have to do in order to move to the other group? It will tell me, go to this direction. So basically, I'm adding something that is orthogonal to the manifold. And being orthogonal to the manifold is just like saying it looks like noise. And so this is why it's so easy to attack neural networks that are classifiers, because with a simple step, small length, and in a specific direction that may look like noise, you change the image in a way that doesn't seem to human person as any change, and yet it is classified differently. This is what happens. What is the remedy for this? The remedy are robust classifiers. So basically, the idea is the following. If this is your data on the manifold, and this is the separating hyperplane that we had before, now let's add adversarial attacks. Basically, per each image, let's compute the gradient and add it and create new examples and give them the same label. If this is a dog, this is a dog, etc. Now, train your classifier using the attacks as well. And so you'll get something that is more brutal. It has to go through all the possible examples. And now you start getting more proper separating surface. Now, if you compute the gradient, what would you get? The gradient of this point, for example, basically asking, how should I change this image in order to make my way towards the other class? It will point to this direction, and this direction tells me, move on the manifold, change the dog little bit by little so that it becomes a cat, etc. So now you get something is known as PAG, perceptually aligned gradients, gradients that have visual meaning in the sense that you are staying on the manifold as you change. So robustness might help in improving the classifier guidance. And so Bahjat Kawar, together with Roy Gantz, worked on this and tried it and came up with the following. First, let me visualize for you the gradients themselves. What you see here are 4 images, the same 4 images left and right. And what you see here are the vanilla gradients and the robust gradients, the vanilla and the robust gradients. This is for time equals 0, basically for clean images. And this is for time equals 300, which is one level of the noise. You know, we start with 1000, we end up at 0. So it's somewhere in the middle. And what you see here is that, first, let's go to the robust line. In the robust line, you see that the gradients are connected to the content of the image. For example, if this is a squirrel and you want to take a derivative, it will highlight the features of the squirrel in order to make it more of a squirrel, etc. for all the elements. Something really fishy happens with the vanilla. Vanilla should have been pure noise, but it's not. And why? Because what they did here is to work with the classifier that has been trained for all noise levels. Turns out that as you train classifier to work with noisy images, it is already partially robust, and so you get better gradients. But notice, better, and yet they are not as good as the robust ones. For example, here you are spread all over, or here you are spread all over. You don't really touch the elements that needs to be changed, or here, definitely when the image is more noisy. So you get better gradients, and with better gradients, if you do the guidance, here is what you get. For example, we start with the same seed and the same random vectors, and we generate images, 2 images, vanilla robust, vanilla robust. In the beginning, everything looks the same, and we keep going, and slowly there is a gap towards the robust. The robust creates slightly better images. I remind you, even the vanilla has a robustness in the classifier because of the training with the noise, and we get slightly better results up to the point where we finish. And in terms of FID, there is a slight improvement from almost 3 to 2.85. So robustness can work, but it's not making a major difference here, simply because in ImageNet, even classifier guidance works quite well. But in other situations with bigger images, etc., this guidance starts to break off, and people kept searching for alternatives. And this brings me to the next kind of guidance, the classifier-free guidance. Okay. This is the score that we wanted to approximate. It's a conditional one. We wanted to condition the score on the given class that we would like to produce. How do we do it? Before we suggested base. Let's now do something different, something that I already mentioned. Let's use a conditional denoiser. This is the denoiser that gets in addition to the noisy image and the noise level, it gets the class itself. Okay? The implication is the denoiser knows which class it serves, and hopefully it will do its service to the point where the denoised image is taking the knowledge of C into account in the best possible way. It's very easy to apply, just train this. On the downside, you don't really know what you get. One thing that might help you as a sanity check is the following. You have a denoiser here that gets as input C. You have actually, in training this denoiser, what people typically do is to train a denoiser that can be conditioned or unconditioned jointly. So there is an option to put C as null, and then the denoiser is regular, or C that is informative, and then the denoiser takes it into account. Now, here's what you have to do in order to make things sensible to you. You have to show to yourself the error of the denoiser, the error, the true image minus the denoised image, averaged over many, many noise realizations and many, many images as a function of sigma. And you get some sort of curve. Okay, this is the performance of the denoiser per every level of sigma noise. Now, if this is without C, if the same machine getting C is creating a curve that is crossing above, you are in bad shape because you have a denoiser that got more information and chose not to use it and in fact wasted. So you must make sure that your curve, the red one, is below the green one. And this is just a sanity check, okay? And again, as I said, when people train this machine, they train basically one denoiser that can serve both as conditional and unconditional. By simply choosing C equals 0, this is the null decision or don't know, and then the denoiser just denoises an image without any reference to a class. And then 1 to 1000, it creates the conditional denoising. Now, why are we doing this? Because of the next thing that I will explain. But before that, this is the paper that introduced the classifier-free diffusion guidance. Let's read the abstract. Classifier guidance is a recently introduced method to train off mode, coverage, and sample fidelity in conditional diffusion models post-training. In the same spirit as low temperature sampling, etc., etc. Let's see. Classifier guidance combines the score estimate, just like we saw, of the diffusion model with the gradient of the image classifier, and thereby requires training an image classifier. It also raises the question of whether guidance can be performed without a classifier. We show that guidance can indeed be performed by a pure generative model without such a classifier in what we call classifier-free guidance, and let's see what they do. This is a paper by Jonathan Ho and Salamans from Google Brain from what? A year and a half ago. Here is the idea. Remember, this is the approximation of the score that we had, the regular score plus the extra conditioning and multiplied by the scale that people found that is useful in order to extremize the behaviors that they are getting. Okay, so this is what we are after. S, again, the scale. Can we do this? Can we achieve this without a classifier? The answer is yes. Here is what we shall do. I remind you, the conditional score, because of base, is the regular score plus this conditioning without the S. Okay? Just simple base gives us this equation. The blue part the red part is easily calculated using a regular denoiser. The blue part is easily calculated using a conditional denoiser. Okay? So what differs between the red and the blue is only the choice of the denoiser being used. And I remind you, it's the same neural network, simply with a different entry for C. Here you put C equals 0, and therefore this denoiser is free of conditioning. Okay? Now, given the red part as an expression of denoisers, and given the blue part as an expression of a denoiser, you can actually compute this part, the classifier guidance, basically the blue minus the red. This is exactly what I'll do now. Here is the blue, here is the red. Let's do blue minus red and get the classifier guidance. What is it? Take these two expressions. Basically, we get the difference of the two denoisers. This is exactly the difference between the two curves I've shown you, okay? Up to a scale factor. Okay, now take this, multiply by S, and add it to the regular score. And what do you get? You get, here is the score, here is S times this expression. And we get now a total expression that uses only denoisers of two kinds and can have any scale that you want. Okay, let's do the algebra a little bit. So this is what you get. It's 1 minus s times regular denoiser plus s times conditional one. And all this serves as the combined denoisers minus x in order to give you the conditional score. So what do we get here? We get that if s equals 0, it's a regular denoiser, and therefore it's a regular synthesis of images without any conditioning. If s equals 1, this is the regular conditioning score. If s is bigger than 1, you are sharpening the effect. Okay? This is called barycentric combination because it's 1 minus s and s, so the sum is always 1. Why not convex combination? Because I'm allowing s to go outside the interval 0 to 1. Okay. And it works. Let me show you from the very same paper that I mentioned. They did it for the following example. This is s equals 1, and they are creating images of specific dog. I forgot the name. And husky dog, yes, husky. And as the s grow, look at the effect. The images are more sharply defined as husky dog, whereas here, some of them are hardly so, or harder to classify. So this is the effect of growing s, okay? Or more accurately, the effect is that you get better precision, less recall. Better precision means very good images, but you are not covering all the possibilities of images. Okay. This is, these are the two parts that define classifier guidance and classifier-free guidance. And the next part will be the text-to-image part. Let's take a break now. Good. So we proceed with the last chapter in this presentation in today's meeting, text-to-image methods. We have seen the general story. We are being given a prompt, a caption, T. This is how we denote it. And we would like to create an image that matches it to a large extent. You have to understand, this is nothing short of amazing. I mean, 10 years ago, if you would have asked me to do something similar and asked me to use all the machinery in image processing, we couldn't have done nothing that comes even close to this. And suddenly it is possible. Not only possible, it works amazingly well. During 2022, a year and a half ago, a burst of such techniques came up. This table shows you the main techniques. They are not the only ones. DALL-E 2 from OpenAI, Stable Diffusion from Stability AI, Imagen from Google, Midjourney with their solutions. And we will talk about these solutions and how they operate and what they do. And we will focus mostly on Imagen simply because it's a scientific paper. And so we can dive into the details of it and talk about the choices made there. So these are the tools we are talking about: DALL-E, Imagen, Midjourney, Stable Diffusion. Imagen and DALL-E are research papers, and they are trained on private data sets that you and I don't have access to. Stable Diffusion is the only open source, which explains why it is so popular and being used by everybody. The open source is not the training data itself, as far as I know, but the code, the diffusion algorithm itself. Midjourney is a pay-to-use application, and the image quality by Midjourney is agreed by many to be the best. All these algorithms are generally very similar. They're all based on diffusion of the sort we have seen, with conditioning of the sort I'll show you in a minute. And yes, there are many, many delicate differences, and of course, the training data. The training data, you have to understand, is everything. If you have larger training data, and you have higher computing power, you can get better and better results. Again, we will dive into Imagen in order to give you a glimpse into what such a method creates. But just before going there, let me show you kind of images you can expect to see. So here are images from DALL-E 2. Let's go through them because they are amazing. Vibrant portrait painting of Salvador Dali with robotic half face. Just look at it. A Shiba Inu wearing a beret and black turtleneck. A close-up of a hand palm with leaves growing from it. So this was DALL-E 2. Let's move to Stable Diffusion. A painting of the Last Supper by Picasso. Look at this. My God. I mean, this belongs in a museum. An epic painting of Gandalf, the Black, summoning thunder and lightning in the mountains. A sunset over a mountain range vector image. So you actually can talk about the style of the image. Imagen. Teddy bears swimming at the Olympics 400 butterfly event. A cute corgi lives in a house made out of sushi. A cute sloth holding a small treasure chest. A bright golden glow is coming from the chest. And Midjourney. Midjourney is somewhat different. Midjourney is so sophisticated that you can actually specify the camera that took the image in order to get specific F number kind of results, etc. Cyberpunk anatomical heart model, white background. Or the mind is like a lotus, white. I mean, it's poetry, turns into an image. Or this one, 1920s Paris cafe, gorgeous, thoughtful female dinner, enjoying coffee, Friday night, close up, noir ink wash, fantasy. And you get this one. Just amazing. And now let's dive into Imagen. So this is the paper that came in May 2022 by a large group from Google Brain, the Canadian group. And let's see what they did. Let's read the abstract. We present Imagen, a text-to-image diffusion model with an unprecedented degree of photorealism and a deep level of language understanding. Imagen builds on the power of large transformer language models in understanding text and hinges on the strength of diffusion models in high fidelity image generation. Our key discovery is that generic large language, etc. Never mind. Let's move on. Okay, and we will see the details in a minute. So, honestly, the work itself is boring because it has almost no surprises. It's almost everything that you would have expected. So let me show you the details. You start by taking the prompt and feeding it into a language model that turns it into a fixed length vector that embeds the text. This vector is the one that will be fed into the denoiser in the training and in the activation. And the diffusion take this embedding vector and generates an image from pure noise. Okay, so basically a golden retriever dog wearing a blue checkered beret and a red dotted turtleneck will turn into this image. Now, how does it work? First, you have to know they do it in 3 levels of resolution. They don't jump straight at the image of 1024 by 1024. They do it in chain of operations. They start by a diffusion model that generates a 64 by 64. So this is more civilized training that does most of, if you think about it, most of the effect of turning T into an image. Okay, once it is ready, it is taken, the image itself, and super resolve, basically increase the resolution using the tools that we will see next week for inverse problems, and using the prompt itself, and yet another diffusion conditioned on both this image and the text will give you the next level to 256 by 256, and yet another step like this, and you end up with a final image. Okay, and observe that T is fed to every one of those diffusions. Why? Because some delicate details in the prompt might not be served well in this stage, so they will be filled up later on. Okay, so let's talk about the first generator. The first generator creates an image of size 64 by 64 that corresponds to the prompt. Regular conditional synthesis. This is what we called classifier-free guidance. So basically, they design a denoiser that gets no conditioning, and yet the same denoiser with conditioning on the text. They train on many, many pairs of images and prompts in order to get the connection between the two. And they do classifier-free guidance with S equals 8. So they squeeze S truly very high in order to get pronounced results. Okay, and they show in the paper what happens if S is smaller. You get images that are less serving well the prompt itself. So they found that they need to push S. They are not the only one. I think Stable Diffusion is doing the same. The later steps are basically solving inverse problems with prompt. Why inverse problems? Because given the image of size 64 by 64. I'm asking what is the image of size 256 by 256. So I'm increasing resolution by 4 in each axis. It's a super resolution problem, but with knowledge of the prompt. How they do it, we'll see next week when we see how inverse problems are solved. But basically, they do the expected approach. A denoiser that gets conditioning on this and just trains in order to match the output images as best as it can. And once you have these denoisers, you are free to go. More details. Imagen works with both DDPM and DDIM, both 256 steps. So with randomness and without randomness. But I remind you, even without randomness, it is random because the initial vector is random. The denoiser itself is unit plus attention. This is what most commonly used today in diffusion methods, including stable diffusion. Training is using 1 million pairs, training of the denoiser. 1 million pairs of images and their prompt. So you show me many such pairs, and the images are brought with different levels of noise, and the denoiser knows what to do and knows how to take the prompt into account. I remind you, the prompt is basically long list of numbers, I think 2,000 numbers, I'm not sure, that embeds the prompt. Now let's talk about this embedding. You take this text and turn it into a vector of fixed length. How does it work? You use a language model. And there are many language models out there, and they tried several of them. They have tables and comparisons, and eventually they recommended one of two things: either CLIP, a language model that came from OpenAI and it's free source, or XXLT5 that was developed by Google that is more monstrous and therefore performing better. We'll talk about CLIP in a second. There was a question? Okay, so let's continue. So let's talk about CLIP. How CLIP works. The idea is the following. Imagine that you have a data set of many images and their prompts. In CLIP, they had 400,000 such pairs, okay? Here is what they did. They trained text encoder and image encoder. This is a language model. It gets the language and turns it into a vector of length 2,000. They take the image and turn it into a length 2,000. In order to create an agreement between the prompt and the image, they asked for alignment between the vector that is coming here and the vector that comes here. So basically, you do sort of inner product between the embedding of the image and embedding of the text, and you ask the main diagonal, so the prompt that corresponds to the image, to give you high value, and all the off diagonals to be nearly zero. Okay, so it's a contrastive kind of training. So pairs of images and their captions are given, and the goal is to train both modalities, train the text and the image encoders. CLIP does so by embeddings and doing it in a contrastive way. And here is what they do. They use the cosine similarity. So they take the inner product, but normalized. And so it's a value between -1 and 1. They take the cosine of it. And this is a value between -1 and 1, but we don't really care about the negatives. We want to push the main diagonal to be nearly 1, so that the IK and TK will be perfectly aligned in their angle. And we want the values off diagonal to be nearly 0, nearly orthogonal, so that the inner product is nearly 0. So this is the idea. So every batch that comes, you push this to the specific group of images that you have. And this creates the two embeddings. Now, once you have the two embeddings, if you need to take text and turn it into an embedding that will serve for conditioning, you use this block here, the text encoder. This is it. This is the CLIP encoding that they mentioned. Okay? Now, there is something called CLIP score, which is lovely, which can be used in order to assess machines that are generating images based on prompts. So imagine that I'm giving you many prompts and I'm generating images. How can I give you a grade for the success? Something like FID. How do I do this? I can actually take the embedding of the prompt, the embedding of the generated images, and see how much they are aligned. You see the cosine similarity between them. So this is known as the CLIP score. And I'm mentioning this because we will be using it in 2 slides or 3. Okay. Thresholding policy. Here is something that nobody speaks about. You run the ALD or the DDPM, doesn't matter. And this is the algorithm. These are the steps. And you replace this yellowish part, the conditional score, with this horrible looking expression that is the classifier-free guidance. Remember, we have two denoisers, conditional one and regular one. And and then something really strange happens. Because of the S here that is really big, like 8, the values of this expression are so extreme that the image xk plus 1 goes out of the domain of the range of permissible values. If the permissible values are typically between -1 and 1, you might get values like -2, -3, +5, etc. Now the question is, what do you do with them? This is known as the thresholding issue, and nobody speaks about it in the literature. So here is what they did. They approached it and they suggested something called dynamic thresholding. Big name for something really plain. Here is what they do. If the input value of the expression that we saw are in the range -1 to 1 and may go outside, static thresholding says everything that goes above 1 will become 1. Everything that goes below -1 becomes -1. This is the static. The dynamic option is simply this. You create another threshold, something like 2, 3, whatever. This is T. So you threshold, and once you finish the thresholding, you divide by T so that you come back to the interval -1 to 1 in the output. So this is what they did with T bigger than 1. This is their dynamic thresholding, and they have shown that it really works well. What you see here is what happens with their algorithm where there is no thresholding. You see that images are either thrown to the very bright values or to the very dark values, and so many of the images are just lost. If you use the static, it starts to work well, but it does lose some of the images. If you do the dynamic, you get better results. And so they went for the dynamic option. In terms of performance, how do you evaluate such an algorithm? What is it that we are after? We would like to get good-looking images, and so FID can play a role here. But we also want to make sure that they match the prompt. I mean, if you just create images that are unrelated to the prompt, you have failed. And this is exactly where clip score will come in. So here is what they did. There is a large data set called COCO that has images and prompts. They took 30,000 random choices of prompt from COCO and generated images from them. So they have now 30,000 generated images that correspond to specific prompts. For quality, what they did is to take those 30,000 versus the true 30,000 images that correspond to the same prompts and created FID score and computed the FID. And they did that for themselves and for the competitive methods. And for assessing the match to the prompt, they did the clip score. So take the prompts, feed them to the clip encoding, feed your images to the visual encoder, see how the score between the cosine score between the two vectors is looking like, and report of it. And this is what they did. They did much more than that. They had also human evaluations that I don't want to dive into. And here are some results. So here is the experiment with FID. Basically, as I explained, 30,000 images driven by prompts from COCO. By the way, you see here that there are competitive methods that were based on GANs, okay? But they are not truly competitive. The better techniques are these ones, and notice that they are in a different column. They are under the column 0 shot. And what does it mean? All these methods trained on COCO and tested on COCO. This method trained on separate data sets and tested on COCO. And so they are called 0 shot. As you can see, Imagen gives an FID of 7.27, which is way better than DALI 2 and way better than Glide. And God knows how Stable Diffusion fits into this table. Maybe the paper itself shows it. So this is the FID part. As for the clip score, what they have shown is 3 graphs, one that corresponds to the effect of the text encoder, the effect of the unit for the denoiser, and the effect of the thresholding dynamic versus static, what I've shown you. What you see here is the following. In all those graphs, it's FID versus clip score. Now, I remind you, clip score, you want to be as high as possible. FID, you want to go as low as possible. So basically here, it's the blue that does the best performance, and it is the T5, the inner model that Google has. Clip score is not even here, but it's eventually what is used. In this case, the UNet, it really doesn't matter. So all sorts of complexities of the network, and all of them are equally performing, with a slight advantage to the bigger ones. And here the dynamic is performing better as expected. Okay. This topic is hot. I mean, I'm reading news these days and it's all over the news. And the question is where things are going now. You could talk about speeding up these algorithms because they do take time. You can talk about introducing editing capabilities, and already work has gone in these directions. You can talk about generating video, generating audio, generating 3D shapes, all sorts of things based on captions or based on other conditioning. So a lot of things. And let me just show you how hot this topic is by showing you press releases from the recent days. So here is a press release from what? 2 weeks ago. Google introduces a new AI model for video generation, Lumiere. This is basically a diffusion algorithm created by a team that sits in Israel, Google Tel Aviv. By the way, Tomer Michaeli from the EE department is part of that team. And they created a diffusion algorithm that generates videos. So 2 weeks ago. Here is a press release from what? 3 days ago? OpenAI just revealed new software that lets you create realistic video by simply typing a descriptive sentence. Okay? It's amazing. 3 days ago. OpenAI. Here is another news expert. Apple is somewhat behind. We have to say Apple is behind in this field. Look what they are publishing a week ago. Apple made an AI image tool that lets you make edits by describing them. So basically, by describing textually what you want to achieve, they create changes to the generated images a week ago. Here is press release from Stable Diffusion. Stable Diffusion basically released something called Stable Cascade, a new version of their code that operates way better than the previous one. Stability AI tries to stay ahead of the pack with a new image generating AI model. 3 days ago. In fact, 3 months ago, Stable Diffusion adds video generation. Okay, so it happens in all fronts. And the last, I think, Midjourney leaps into AI video creation. From a month and a half ago, the AI image generator Midjourney will begin training. Look, they announced that it will begin training its video model in the upcoming days. So it's not happening yet, but they see the competition and start being stressed. So they inform everybody that they are in the game as well. So the topic is really, really, really hot. This is where I stop today's lecture. Questions?